Good afternoon. Today we will study the next topic with respect to functions, which is recursive functions. So recursive functions, basically we are studying about those functions whose arguments and values are natural numbers, and such functions are also called as number theoretic. And also in general we shall consider number theoretic function of n variables, which will be denoted as f of x1, x2, and so on up to xn. From now on, we shall not mention the fact, although it is assumed throughout that all the functions are number theoretic. Now, any function can be written in these two ways. One will be the total function, and the other will be the partial function. So basically, there are two types of function. So let's see the first type, which is total function. So total function in general, a total function is usually just another name for a regular function. So when we are speaking about any function, it is usually a total function. Why do we use the term total? The term total is used to define or to make it clear that all the elements in the domain. So if you remember, this was our domain and this will be our codomain. Since all the elements are mapped, the codomain and range are the same. So the term total is used to make it clear that the function is defined for all elements in its domain. Okay, but in partial function it will be something different. So that is the reason we use the term total. So total function is usually another name for our regular function. Whatever function we have studied in the earlier classes, the total function is the same as that. So now we will study, the important thing to study is partial functions. So let's study partial function, then we will understand why do we call it total. So a partial function is only a function that only partially works. So what does it mean by that? Suppose if in your domain you have 4 elements and only 3 are being mapped to the codomain, then it is known as a partial function. So over here b is left, we have not mapped b. Okay, so basically if your domain was represented as D, then from D you're taking only a subset S. So S is a subset of D and your partial function is denoted as S to your codomain. Okay, S to C. So whenever we consider only few of the elements of the domain, then it is known as a partial function. But sometimes not every input matches to an output. So technically, if one or more inputs aren't linked to an output value, then it's not a function. However, there is an exception made when the function mostly works. So this is your function, and this kind of function is known as a partial function. Now, in this case, let's see an example with the same for total function and partial function. Suppose if we have a function f of x comma y is equal to x plus y, and it is defined for all x comma y belongs to n. Okay, for all x comma y belongs to n, and this kind of function is known as a total function. Okay, why? Because whenever you take x plus y, if you take x comma y belongs to n, each of the values of this function will be mapped in the codomain. Okay, while with respect to the same, if I instead of x plus y I take the function as x minus y, then it will be defined only for a few values. That is, if x comma y belongs to n, and if we want to map the elements, then whenever x is greater than y, then only it will give us a natural number. If x becomes less than y, then we will get a integer, and integer is not in our codomain. So in that case, elements of your codomain will elements of the domain will not be mapped entirely. So in that case it is known as a partial function. Okay, so x plus y is considered as a total function, while x minus y is considered as a partial function. Now with respect to this, every total function of n variables, if we are taking a function of n variables, and then that is given by a set of 3 initial functions. So we have a set of 3 initial functions. So the 3 initial functions, I'll give the names first and then we will see each of them individually. So first is zero function, then we have successor function, and then finally projection function. What do you mean by zero function? The function whose value is zero for every element in its domain. The term is usually applied more specifically to the function where if the function is from n to n, then for which z of n is equal to 0. So these initial functions are very important for your primitive recursive function. We use it in primitive recursive function. Okay, so for all n in n, the set of non-negative integers, or basically your natural numbers, the function is a basic to the theory of recursive and primitive recursive functions. Okay, so basically whenever your function, or we can simply write it in this way, z is such that z of x is equal to 0, that is your function always gives the value 0. Now what about the next function, which is the successor function? So the successor function, the function s n to n, for which s of n will give you the value n plus 1. So every time in the case of successor function, if you are mapping the value x, it will be mapped to x plus 1. If you are mapping the value x plus 1, it will be mapped to x plus 2. That is, it maps to the next element in the numbers, in the natural numbers. So basically it is mapping to its successor element. Okay, if you remember the terms predecessor and successor, predecessor means the before element, while successor means the after element. So every time you're mapping the successor function, it is mapped to the n plus 1th element, where n is the non-negative integer. And s plays a crucial role in recursive function theory, particularly in the primitive recursive function. Now after that we have projection function. Projection function we will see directly while we are studying primitive recursive function. So let's see the definition of primitive recursive function. So primitive recursive function, a function that can be obtained from certain initial functions by a finite number of applications of composition and primitive recursion. Now what does this mean? Composition we have already studied for two functions, f circle g and g circle f. Okay, composition of functions. So if you are applying these composition functions and primitive recursion, now what does primitive recursion means? It means that we use the zero function, successor function, and projection, or it is also known by the name generalized identity function, and where all the functions are defined on natural numbers or non-negative integers, that is only positive integers. Now primitive recursive functions, they are also total functions, and they are defined in a simple way by induction. Induction is when we take the first element and we create a proof for n is equal to 1, then some number n is equal to k, and then n is equal to k plus 1. It is induction here refers to your mathematical induction. And also there is also a notion of primitive recursive set, namely one whose characteristic function is primitive recursive. Okay, so let's see the primitive recursive function in detail. A function f of x1 comma x so on up to xn. So if you notice, when we studied our normal functions, we just used to write f of x, that is the only variable on which the function was defined was x. But here we will have more than one variable, that is x1, x2, and so on up to xn, and it is primitive recursive if either it is a zero function, that is f is the function that is always 0. F of x1, x2, and so on up to xn will give you the value 0. This is denoted by z when the number of arguments is understood. So the rule for deriving this kind of primitive recursive function is known as the zero rule, or our zero function. And now what about it being primitive recursive? It can be primitive recursive even if it is a successor function, that is x1 and so on up to xn will give you xi plus 1. So if you take f of xi, then it will give you the value xi plus 1. So this rule is known as the successor rule or the successor function. Now what about the projection function? F is the projection function, that is f of x1 and so on up to xi. Then it gives you the codomain is taken as xi, and this is basically what we are doing. Whatever we have in this domain, we are taking the same element in the range, so it is being projected. So if we have taken f of xi, it can be also written as an identity. That is, if we are taking xi, then we will get the same element xi. So this is denoted by pi subscript I. When the number of arguments is understood, this rule is known as the projection function or the projection rule, or also known as generalized identity function. Generalized identity function. Now, based on this and two more primitive recursive rules, so f is defined by the composition of previously defined primitive recursive functions. That is, if g1, g2, and gk are all primitive recursive and h is also primitive recursive, then f is written as h of g1 of x1, x2, and so on up to xn, and we take the composition of all these g1, g2, and till gk. This is primitive recursive. This rule for deriving your primitive recursive function is called the composition rule. So earlier when we have seen the composition of function, we had only f circle g and we were defining it by taking h. But over here, instead of the same thing, instead of that, we are taking f and we are taking h of composition of g1 circle, g2, and so on up to gk. Okay, so this is what our primitive recursive composition application of your composition function is taken as. Now after that, f is defined by recursion of two primitive functions, that is g and h are primitive recursive, then the following function is also primitive recursive. Okay, and now this rule is called as the recursion rule, or it is also known as a primitive recursive rule. Now based on this, we will see an example. So a function f is called primitive recursive. A function f is called primitive recursive if and only if it can be obtained from the initial function. So we had three initial functions. So from that, those three initial function, even if we have one of them, from the initial function by a finite number of operations of composition and recursion. So a function is all called as primitive recursive if we are using our initial functions and performing either composition or recursion on the same. Now after that, we have to show that this function f of x comma y is equal to x plus y, whether it is primitive recursive or not. So we know that it is a total function. Now for this, what we can do is we can take x plus y plus 1. Okay, and I'm adding to y plus 1. Instead of y, I'm keeping it as y plus 1. And then it can be written as x plus y plus 1. So this can be replaced as f of x comma y plus 1 is equal to f of x comma y plus 1. So in this case, it can be written as the function, if I'm taking y is equal to 0 over here, then let me write this over here. So if I am taking y is equal to 0, then f of x comma 0 can be written as simply x. Okay, and f of x comma y plus 1 is written as f of x comma y plus 1. So this means that if we see our for y is equal to 0, it is satisfied. For y plus 1 also it is satisfied. So this function can be called as a primitive recursive function. That is, what are we basically using here? We are using the inductive step function. Okay, we are using the inductive step function, and by that we can easily say that it is primitive recursive. Also, we'll see the definition for recursive function. A function is said to be recursive if and only if it can be obtained from the initial function by a finite number of applications. So this is important, that is our application or the number of times we are using our initial functions should be finite, by a finite number of applications of the operations. Which operations should we use? We can use composition or recursion or even minimization. So what do you mean by minimization? If we are getting for a minimization, we are supposed to check whether we have the element in our function or not. If it exists, then we write it as g of x1, x2, and so on up to xn comma y is equal to 0. Otherwise, we write it as undefined. So that is minimization. And these all operations should be done over your regular function. Okay, so this is your recursive function definition. There are no examples as such for the same. You just have the definition. Now moving on to the next topic. The next topic is lattices and its properties. So in the earlier lecture, we have already studied Hasse diagram and what does a lattice mean. So before we study the properties, so in this case, a basic difference we have to know is that in order to emphasize the role of an ordering relation, so we studied about relations, and relations are ordered pairs. So whenever we are studying about ordering relation, a lattice is introduced as a partially ordered set. Okay, so lattice is basically your partially ordered set, and for this we are supposed to study lattice as an algebraic system. That is, we will study a few of the properties for lattices, both the lattice and also apart from that Boolean algebra have important applications in the theory and design of computers. So that is the reason we are supposed to study lattices. So here we will study lattices as partially ordered sets and they will satisfy certain properties. Now in this case, if you remember, we studied lattices along with the concept of least upper bound or lowest upper bound and greatest lower bound. And for that, we will again see the definition of lattice first. So let's see the definition of lattice first. So a lattice is a partially ordered set. And if you remember, for poset, we will write the symbol less than or equal to. L comma less than or equal to, in which every subset A comma B consisting of two elements of your partially ordered set has a least upper bound and also a greatest lower bound. So for every element, if you remember, we studied that every pair of elements should have a least upper bound and a greatest lower bound. So now that is denoted, the least upper bound is denoted by A or B, or it is also known as the join. Okay, this symbol is known as the join, and this is for least upper bound. Similarly, the meet or the meet for greatest lower bound is denoted by inverted V, and this is called the meet of A and B. Now based on these two, join and meet, we have the properties of lattices. Before that, let's see an example of the lattice that we have seen already. So over here in this example, these were the two examples that we have already seen earlier. So if you take any two pairs in the first example, each and every pair will have a greatest lower bound and least upper bound. But if you take the next F or G, that is, it won't have a least upper bound. So here or represents the join and it won't have the least upper bound. Now, what are the properties of the lattices? So the properties of lattices are as follows. First and foremost, we have idempotent property. Idempotent property is that if we perform join or meet of any of the greatest lower bound or the least upper bound, then it is known as an idempotent property. That is, we get the same A. That is, if we either perform join or meet. Now, similarly, if we have a commutative properties, these were the properties that we have already studied with respect to propositional logic. So the same properties we are studying again, but here instead of the propositions we are taking lattices. So commutative property, if either we are performing the join or meet of the lattice, then it will be equal. That is, even if the order is changed, it will give us the same result. Similarly, we have the associative property. Associative property is basically with 3 elements and it is similar to commutative property. And lastly, absorption property. If we are using two different, that is, if we are using join and meet of both the lattices for any binary operation, if we are either performing join with 2 elements and then meet with the other element, then it will give us the same result. That the next topic is algebraic structures. What do you mean by algebraic structures? So to define it, what we can consider is, we can consider a system consisting of a set. So it is a system consisting of a set and one or more operation, n-ary operation. Now, what do you mean by n-ary operation? That is, it can be a binary operation or a ternary operation, or we can have even n operations performed. So of a set and n-ary operation on a set, it will be called as a algebraic system. So this is called as an algebraic system or simply algebra. Now this is denoted by, this algebraic system can be denoted by a set S and all the operations that are being performed. So these are the F1, F2 denotes the operation. So this is your set, where S is your set or a non-empty set, and F1, F2 and Fn are the operations on S. Now, as a part of the system, we can also include relations on S, which are not necessarily operations, since the operations and relations on the set, so operations along with the relation plus the relation denote some kind of structure. So the algebraic system is also called as an algebraic structure, and it is also possible to consider more than one set. So instead of a single set, we can consider more than one set, or maybe simply sets, and we can perform operation on these sets. Now we are not restricting ourselves to only n is equal to 0, 1 or 2 operations. We can consider more algebraic systems simultaneously. And whenever we are considering more algebraic operations, we use the symbol either star or a small circle, which we were using with composition of functions, and these type show that denote an operation. Now, on what kind of sets can we consider the algebraic system? So let's see the same. So algebraic system can be considered on a set of all natural numbers, on the set of all integers, set of all rational numbers and real numbers. Now, what do you mean by the operation? The binary operator which is usually used is the star symbol, and it is said to be a binary operation or a closed operation on a non-empty set A if A star B is equal to some number or some value and it belongs to A. So whatever the result of the operation is, it should also belong to the same set for all A comma B belongs to A. So this is known as the closure property. So the set N is closed with respect to addition and multiplication. What does this mean? So suppose if you are taking the set of natural numbers N, and if we are taking any two numbers in the set of natural numbers, consider them as a comma b. If you perform a plus b will give you the result c, and that c will also be in the set natural numbers. Similarly, if you take multiplication also, a into b, it will give you some result d, and d also will be, d will belong to the set of natural numbers. So this is known as the closure property. That is, whatever result you are getting when you are performing the operation, that result should also belong to the set that is being considered. So that is your binary operation with respect to the closure property. Now the next is, and what about subtraction and multiplication in the case of the set n? So if you perform a minus b, and if a is lesser than b, then you will get a negative value, and this negative value does not belong to your natural number. So in that case, uh, it is not giving you the closure property with respect to subtraction, and similarly with respect to division also. If a divides b and it is giving you some value in decimal numbers, then it won't give you, it is not subtraction and division does not satisfy the closure property. So that is but not with respect to subtraction and division. Now what do you mean by an algebraic system? A set A with one or more binary closed operation defined on it is called an algebraic system. Example, so that is, it should satisfy the closure property: natural numbers with the operation plus, integers with plus and minus, real numbers with plus, minus, and multiplication. They are all algebraic system. Now what are the properties of algebraic system? Commutative. Suppose let star be a binary operation on set A, and that is said to be commutative if a star b is equal to b star a, and a comma b belongs to a. So that is commutative property. Similarly, we have associativity. So if associativity is basically with three elements, a star b star c is equivalent to a star b star c, and the operation is said to be associative in A. So ABC should belongs to A. Identity element is, suppose we can consider any element E, and if we are performing the operation with some element A, then it should give you the same element A. So for natural numbers with the plus sign, A plus 0 will give you A again, and 0 plus A will also give you A again. So this 0 in the case of natural number is the identity element E. Similarly, if you take real numbers with multiplication, in that case, one is your identity element. So that is basic mathematics which you already know. So for an algebraic system, the identity element, if it exists, is unique. So for any algebraic system, the identity element will be unique. And also, what about inverse? Let A star be an algebraic system with identity E, then let A be an element in A, and element B is said to be in inverse of A if it is giving. So if we write in the case of uh, 5 minus 5 is equal to 0. So minus 5 is the additive inverse of A. We call this as additive inverse in mathematics. So that is here simply minus 5 is the inverse of 5. And if both of that with the operation, whatever operation is being taken, if it is giving you the identity element, then it is known as the inverse. The next is semi-group. So what do you mean by a semi-group? In this case of semi-group, if the operation is associative, if we are taking an algebraic system and it is said to be semi-group, if it first it is a closed operation on A. So this is basically for any algebraic system, it should satisfy the closure property. Apart from that, in the case of semi-group, it should also satisfy the associative operation. What was the associative operation? If I take X, and if your operation is circle, so X circle Y circle Z is equal to X circle Y circle Z, or X of Y of Z. So this is your associative property. It should satisfy this associative operation for all ABC in A. Example, natural numbers with the addition operation is a semi-group. Natural numbers with multiplication is also a semi-group, but natural numbers with minus is not a semigroup. Also, the next is a monoid. So what is a monoid? An algebraic system A comma the operation star is said to be a monoid if the following conditions are satisfied. So the first condition will obviously be the closure property, that is it should be a closed operation on A, and the next is an associative operation on A. So algebraic system is said to be a monoid. So basically this monoid should also be a semi group, and apart from that it should satisfy one more property. So that is the first two properties of your monoid are the same as a semi group, so it will be a semi group. But the third property is that there is an identity in A. So in other words, basically if you have the monoid, it should have an identity element. There exists an element E which belongs to your set A such that X operation E is equal to E operation X is equal to your element X. So that is your set should have an identity element, then only it can be called as a monoid. Next, show that the set N is a monoid with respect to multiplication. So let's see the solution. So what do you mean by our set N? Set N is a natural number. So first and foremost, we have to check for the closure property. What do you mean by that? We know that the product of two natural numbers is again a natural number. So whenever you multiply A into B, it will give you some natural number which is in our set. So it satisfies the closure property. Let A, if that is A dot B is equal to B dot A for all A comma B belongs to N. Now multiplication is a closed operation. What about associativity? That means A into B into C is equivalent to A into B into C. So this over here is a associative. If you associative property is being satisfied if we have our natural numbers set. Now identity. So for identity element, we have 1 as the identity element. In the case of natural numbers, any number if multiplied with 1 will give you the same result. So in that case, our set with multiplication, our algebraic system with multiplication is a monoid. Okay, identity element exists and 1 is the identity element, hence N is a monoid with respect to multiplication. So the next topic is groups. So basically group is an abstract algebraic system. What do you mean by an abstract algebraic system? So whenever we are studying about group theory, it is exclusively based on physical sciences and in computer science. And group theory, we know, we have already seen that we know what is a semi group. So based on that, we will see what a group means. So if you just recall that we have seen semi group, and an algebraic system S comma the operation star is called semi group if it satisfies two properties. What are the two properties of semi group? The first one is the binary operation is associative. First and foremost, for any algebraic system it should satisfy the closure property, and then for semi group specifically we have associative property. And apart from that, we have seen something known as monoid. So monoid was the same with the two properties of semi group had to be satisfied, so closure and associative. And then finally we had the identity element. That is, the set S should contain a identity element E. Now what about a group? For a group, it should have all the three of monoid, that is, it should have closure and it should have associativity, identity, and along with that it should also satisfy the property of inverse. So that is, four properties should be checked for group. And so a group is an algebraic system in which the binary operation star satisfies on these three these four conditions. So closure is generally not included because it is the general property of your algebraic structure. But apart from that, it should satisfy associativity, identity, and inverse. So let's see the definition. Group an algebraic system G comma star is said to be AS. And one more thing, this set can be anything. There is no restriction of an alphabet with respect to the name of the set. Is said to be a group if the following conditions are satisfied. Star is a closed operation. It is an associative operation. There is an identity in G, and every element in G has an inverse in G. So this is known as a group G. Now with respect to that, we have something known as an abelian group. That is, a group G star is said to be abelian, or it is also known by the name commutative group if it is commutative, that is A star B is equal to B star A. So this is known as a abelian group. Whenever we are studying about algebraic system, so it can be said in this way, or it can be represented in this way, that is, algebraic system is an overall structure. Now if that is, it satisfies the closure property. Now if we add another property to it, associative, then it is a semi group, then closure, associative, and we added identity. It was considered as a monoid. So algebraic system is a set. Semi group is considered as a subset of algebraic system, while monoids is considered as a subset of semi group, and this goes on. So in this case, we had closure, associative, identity, and inverse. And abelian group, we added all these four properties. Apart from that, we also had commutative property. So this is the way we can define an algebraic system. Now the next topic is subgroup. A non-empty subset H of a group G comma the operation star is a subgroup of G. What are the conditions if H comma star is also a group? For any group G comma star and E comma star and G, it is a trivial subgroup. Suppose if we are taking an example of 1 comma minus 1 and I comma minus I, it is a group with respect to multiplication. That is, if you are taking these four elements, then 1 comma minus 1 is a subgroup of G, and simply 1 is a trivial subgroup of G. Why are we calling it a group with respect to multiplication? If you multiply 1 into minus 1, it will give you minus 1, and then again minus 1 belongs to your set G, and you can check all the four properties of a group with respect to multiplication, and it will satisfy these properties. So here example, Z plus and Q plus are the subgroups of R plus. And now a non-empty subset H of a group G is a subgroup of G if and only if, what are the conditions? First and foremost, it should satisfy the closure property. So if A comma B belongs to H, then whatever the result of your operation, it should also belong to H, and there should be an inverse element of H. Okay, so this is a subgroup. Now we have two topics which are important, which is homomorphism and isomorphism. So consider the groups G comma star, this is one binary operation, and G1 and another binary operation. Then the function f of from G to G1 is called homomorphism if f of A star B will give you f of A and the other operation plus f of B. So this is your homomorphism. And isomorphism is basically if a homomorphism is a bijection, that is, it should satisfy your 1 1 and on 2, then f is also called as a isomorphism between G and G dash. Then we write G is equivalent to G dash. So this is algebraic structures.